everybody. Hope everybody's doing okay out there. I see a few of you. Let me know in the chat if the volume is okay. I'm trying a different headphone, so I'm just gonna actually listen back in a second. Just give myself a little listen. Okay, that does sound a little bit tinny, but I can't seem to find my good headphone today, my good mic, so we'll have to deal with that. Okay, so today we are in lesson 3 of equilibrium. Okay, and so hopefully everybody had a good spring break. If you haven't been on to our Google Classroom today, you'll notice that I have just added a Google Hangout. So you can join that Hangout. The link is on Classroom, and joining that Google Hangout, you'll see that we can have a sort of a more informal conversation. We can talk a little bit about various things. You can ask me questions if you like there, all of that good stuff. So please feel free to join in there and have a good time. I also am hoping to use that as an online medium to have some other, video conferences and things like that. We can do those all through the Hangouts, and you can leave questions there and all that sort of stuff that you want. Hopefully you're all staying safe out there and not putting yourselves too much at risk. We are currently looking at a indefinite suspension of school. I'm not sure how long indefinite is going to be, but it is what the Minister of Education has said. So as part of that, I understand it, you are going to have whatever mark you had at the end of regular classes. That mark will become your base mark. And anything that you do during the distance education part or during the COVID crisis, it's probably fair enough to call it a crisis at this point. So during that COVID crisis, anything that you do will be added on top of your previous mark. So it can increase the mark, but it cannot decrease the mark. So that's sort of where we're at, if you are wondering. I will be posting, I did finish posting the kinetics units. Remember that we have until June to kind of finish this course. So don't rush anything. If you are able to keep up with the live streams, that's great, because of course that'll let you ask me the most relevant current questions out there. But if you aren't, then that's okay too. We will, just go at your own pace. Finish videos as you finish them. All of these are relatively important for your university careers. So if you're hoping to do university chemistry out there later, then that's what you'll want to be doing doing this content, finishing these units, finishing these various videos and the activities that I post on Classroom, joining us in the group video chats that we'll be having later. Maybe we'll try to post those, try to schedule those for regular intervals maybe. Okay, so today, with all that preamble done, today we are going to be talking about Le Chaltier's principle. This is probably the most important concept in chemistry. It turns out that essentially every single chemical reaction, might be a little bit of hyperbole there, but almost every chemical reaction that we encounter in our day-to-day lives is really are reversible reactions under the right conditions. Some would theorize that every chemical reaction is reversible, It's just that we have to, but just the conditions for that reversing are often not, may be unattainable. But we theoretically could reverse almost all chemical reactions, and that means that all chemical reactions are under some sort of equilibrium conditions. And it turns out that since equilibrium is dependent on concentration and it's dependent on pressure and it's dependent on temperature, that if those three things change, then the state of equilibrium, or the state of the equilibrium concentrations, will modify as well. So this is what was known as Le Chaletiers principle of equilibrium, and it's a pretty key concept that if you can manipulate your chemical system using one of these three concepts, you can manipulate your system using changes in concentration or changes in pressure, which we know is also another way of saying concentration, or through changes in temperature, then you can change the equilibrium values. So these three changes will cause changes in the equilibrium values. So controlling these allows and this is amazing. This whole thing is this is an unbelievable concept to play around with, because this is the way we can take a chemical reaction and really really take it to the next level. Do stuff with it that is control it, manipulate it, change it. This is how you can get more product. You can get more product, more reactant, more anything you want simply by this. I'm going to just make a little adjustment here because I believe that I'm cutting off my screen. Oh, yeah. Okay, just 1 second. There we go. That should be better. All that writing I did over in the corners was cut off there. Okay, so and I'm just going to check, see what's going on over here. Okay. So concentration change, let's start there. So in a system at equilibrium, a change in the concentration of either the products or the reactants present at equilibrium will cause a stress. If you had a system that's already at equilibrium, it already has that ratio of product and reactant that is defined by K. When you add product or reactant, the system will have to reach a new equilibrium point. And so this is going to be done by a variety of ways, but the result is going to be really interesting here. So in a system at equilibrium, a change in the concentration of products or reactants present at equilibrium creates a stress. And this is a word we want to be thinking about, stress. At equilibrium, the ratio of the products to the reactants, the reactant concentrations, is constant. So this is that ratio. This is what we know as, this is our equilibrium constant, right? So this is defined by, so the equilibrium constant defines this ratio. So if you add a reactant, then the reactant will push the equilibrium towards that, towards the formation of products. So one way to think about this is that you have your chemical reaction. It's currently at equilibrium, right? So this is equilibrium. It's got some ratio, some balancing ratio of concentrations of reactant and concentration of product. They are in balance. So if you stress, the system by adding more reactant, and we have the same product, then I don't know if that's not as convincing as I wanted it to be. What if I take this? I'm going to duplicate that, bring it over here. So I've increased the size of my reactant there, and then so that stress means that there's going to be a new equilibrium of so the new equilibrium and the new equilibrium will look something like this. It'll have a slightly larger reactant than before. So duplicate, bring that over. So it will be a little bit bigger, and it will also have an increase in product. Oops. I think I could do a little bit of a better job here. Wait, I'm going to try this one more time. We're going to, the same idea, but we're going to just do it in, I don't know if I had to get rid of the words. Okay, let's try this one more time and do it a little bit more obvious. So I'm going to try my balancing here. Here's my balance beam. Here I'm going to put a little R and a little P. There we go. Okay, so the idea is that you are going to stress the system by adding extra R. So let's just say we added some R's, right? So this is the same as saying that we have one big R. So lots of extra reactant there. And then that stress has to rebalance. So the new equilibrium is going to be with a slightly larger P and a slightly larger R. So we don't have quite the, maybe I should make this one very cartoon sized. Let's make this like a huge R. So we have a huge amount of R. We've added extra R, or extra reactant. That reactant gets consumed, converted into product, and a new equilibrium is reached where both the amount of reactant and the amount of product have been increased, but the product is really, the amount of product being increased is the result of adding reactant. That's really the key. You are able to make more product by adding reactant. Okay, that doesn't, it's not blowing anybody's mind, but it is an interesting concept because what about systems where you had multiple reactants? Well, in a multiple reactant system, you don't have to add extra of both reactants. You only have to add extra of one reactant, and you can still be able to push the equilibrium to the other side. Removing a reactant is always going to drive it in the other direction. So here we have our initial balance beam. Maybe I'm just going to copy and paste here. Okay, so let's copy, paste. So here's our initial balance beam. We're going to stress it by essentially shrinking the R, little tiny baby R, and the P. And so then when it realigns, we're going to be at a case where we have two. Well, they'll be a little bit bigger than that, but they will both be. The P will have gone down, will be smaller, and the R will be back to sort of a middle size. And so we have to shift equilibrium, shift equilibrium. So we're going to shift that equilibrium. And this one we added reactant, so we're going to shift. So that's why this is called a shift to, the first one is called a shift to the right. And here is shift equilibrium left. So we have shifted, we've moved product, or we've moved matter from the product side to the reactant side to rebalance the system, to make those R's and P's the same size. So if we follow this sort of logic, and we paste here, if we add product, then think about adding product as taking this product here, and increasing its size. Just want to increase it. Doesn't want to let me increase it. Okay. Getting notifications left and right here. All right. So if you're adding product, what you're doing is you've found another way to tip this down by increasing the amount of P. I'm going to keep that R about the same. And so with that increase, you're going to need to shift to the left as well. Shift left. And the result will be the rebalancing. In this case, you're going to have a little bit more R than you had before, and you're probably going to be somewhere like this, sort of the R and the P will be back to being equal. So the balance has been shifted. So this is another left shift. Okay, so let's make one more. And this is the one where we are going to take some products away. So this is where we stress. And so we can think about the stress as we have our original. We're going to take some away. So we're actually going to take this guy and we're going to shrink him down. Doesn't want to shrink, but that's okay. We can just make him small. So he's going to be shrunk. And then what will that do to our balance? Well, it will tip it this way, right? Because now the little p is lighter than our r, and so then to rebalance, we need to move matter from the reactant side to the product side. The result will be a little smaller r and a little bit larger p, so that they're back to the same size. So this is a shift to the right. Okay, so that's sort of the teeter-totter analogy. It's pretty typical. So thinking about them as having equal matter is a good way to start. So think about a K of 1, where you have equal matter on the left and the right, products and reactants. If you add more reactant, then the reactant side is heavier, and so you have to move matter over to make more product so that the two even out. So let's consider this reaction here. We have CO2 plus H2, and this is going to be making the bicarbonate. And let's just put those on a little balance beam here. So I'm going to make a little balance beam, and I'm going to put it there. Okay, so I'm balancing out these. If more CO2 or H2O is added to the system, we're going to assume these are gases, by the way. If we add more CO2 or H2O, so one way to think about this is we're going to stress the system by increasing the amount of CO2. which is going to bring this sort of scale down. And so to bring the scale back up, you're going to have to cause a shift of matter towards the H2O3 so that we can respond by creating more C2H or H2CO3 than we had at the beginning. So if more CO2 or H2O is added to the system, the extra reactant must be used up by, and this is a really good connection to our kinetics unit, by increasing the rate of the forward reaction. Remember that rates of reaction are dependent on concentration. So we could use up the extra reaction by increasing the rate of the forward reaction. We could decrease the rate of the reverse reaction. This one doesn't really make sense. Okay, in this example, or we could shift the reaction shifting the reaction to the right. I think this only really makes sense in sort of a relative way. So this is relative relationship. Decreasing the rate of the reverse reaction, let's say, respect to forward. So probably a better way to look at this overall is to think about points 1 and 2. What's really happening is we're increasing or the ratio of forward to reverse rates is changed to favor the forward rate, so that the excess product is consumed, or excess reactant, sorry, okay. If more H2CO3 is added to the system, so in the other case, if we add CH2CO3 or add bicarbonate, there's no voice, really. Did my microphone is connected? I'm still hearing myself in the chat. It's true. Hello, testing. I'm getting sound here. But you're right, I'm not hearing it on my stream here. Oh, just a second, I got my sound turned off. Sorry, I see a message in the chat that I was not getting sound, but I am hearing sound in my my own headphones when I listen back. Okay. I am seeing some stream health alerts. I don't know what to think about this the streaming business. Does seem like streaming, I'm getting some buffering problems. I'm not sure what happens, what is causing those. I have not yet found a satisfying answer to why my buffering is happening. Okay. All right, cancel. Okay, so anyway, so let's so if we add H2CO3, then by adding this bicarbonate, we are increasing the amount of product, and then that increased amount of product is will have to be balanced by producing more reactant, and that will have some effects. I'm just going to quit some background noise here, see if there's anything else I can get rid of that is possibly consuming my bandwidth. Close some of these things. Okay. So let me see. Let's kill my mail. Okay. This is the same idea. So increasing the amount of product means that you are going to increase the rate of the reverse reaction. Remember that the rate of the reverse reaction, so rate reverse, is going to be equal to some constant times the concentration of the products. So if you, in this case, we could be even more particular. We could say that we're talking about H2CO3, and so that would be those would all be erased. The influence of those, or the increase here. Sorry, I get too much stimulus when I'm looking at multiple screens. The increase in H2CO3 means that we would increase the rate of the reverse reaction. We could also be experiencing a decrease in the forward reaction, but really we're just talking about in terms of the ratio of the rate of the forward and reverse. The rate of the reverse compared to the rate of the forward, this rate is now much higher than this rate. So they do appear to be not equal. They're no longer equal. And this will shift the reaction to the left. At some point, you know what, I'm going to type this one just because I want it to be really well done. Hello, type for me, please. At some point, the shift to the left will slow down because the concentration of product will be decreasing, reducing the rate of the reverse reaction. Where can I put this thing that you can actually read it? There's just no space. Okay. Let's probably good enough. So at some point, the shift to the left will slow down or stop, because as you shift to the left, you're moving product away. And as you're moving the product away, then you're slowing, your concentration of product will be decreased, and it will reduce the rate of the reverse reaction. And at some point, you're going to have enough reactant to increase the value of the rate of the forward reaction as well. And so then those reactions will essentially equal out. So as the amount as the concentration increases of one, it will decrease the other, and then they will become equal again. So I am checking everything. Do not see any notes here. Things that are eating my bandwidth. Okay. Well, very strange. Okay. So in the case of pressure change, we have a similar process here, where if we change the pressure of a system, then this will only affect the gaseous products. But you have a similar idea where we know that pressure is related to concentration of gases. So remember that pressure is a measure of concentration for gases. So for the reaction of H2 plus I2 moving to 2HI, the pressure changes would have no effect on the equilibrium position, because each side of the reaction has 2 moles of molecules. So with these 2 moles on each side, 1, 2, and 1, 2, then any change in the volume will have an equal change of pressure on both sides. So the overall concentration is staying constant. Therefore, there is no way to either increase or reduce the number of particles per volume, by changing volume. Therefore, in response to pressure changes, the equilibrium position will remain unchanged. So pressure changes only affect systems that have unequal numbers of moles of gaseous reactants. So this is the key, unequal here, unequal number of moles of gaseous reactants of products. So here, if we have this reaction, N2 plus 3H2 gives 2NH, 2 ammonias. We have 4 moles, and we have 2 moles. So this gives, if we had 1 molar, if we had 1 molar concentration, does that make sense? Well, if we had one liter of gas, then in that 1 liter, if it was just 1 chemical reacting units here, we would have 4 of the 4 per liter on the left and 2 per liter on the right. So that would be very different, or this would be 2 different concentrations. So an increase in pressure will shift the equilibrium to the side with the fewer moles. The products in this case, the reaction will shift to the right. So an increase in pressure means that has a greater effect. So let me just type this out here. So in this reaction, an increase in pressure most likely done by decreasing volume. When we decrease the volume, the reactants have a much larger change than the products in terms of concentration. This will increase the concentration, the reactants, much more, so that the forward reaction occurs much quicker. And by that same token, if we decrease the concentrations, then the left side has a much higher change. So the left side has a much larger change in volume, or in change in concentration. It will be decreased by a lot more, and that big decrease means that the forward reaction, the rate of the forward reaction for the left side is decreased a lot more, probably twice as slow as the reverse reaction. And so equilibrium will have to adjust by shifting to the left, producing more reactants. Another way I like to think about it is by like a squeeze. You're squeezing, and if you squeeze the left, then there are more atoms on the left. So when you squeeze the left, there's a higher chance that they get stuck. They go to the smaller state, the less mole state. And when you pull it open, you open up much more space, and so that space ends up getting filled by the larger number of particles, or the smaller particles. So we can kind of, this is a little sort of, it's not entirely true, but it's good enough sort of analogy. So squeezing the reaction, that's like an increase in P. This promotes formation of less but larger particles. Loosening volume decreases enlarging volume. Loosening doesn't really make sense. Relaxing the squeeze. The squeeze smaller particles form. Space. Something like that. Okay. So for example, let's look at this chemical reaction here. This is the same chemical reaction, isn't it? It is, okay. So what is the effect on the equilibrium if the size of the container is cut in half, but the number of particles and temperature remains unchanged? So we can even go to a full explanation here. We can remember that K is equal to the concentration of our product raised to its power divided by the concentration of the reactants raised to their power. Okay, so what is the effect on the equilibrium if the size of the container is cut in half? So this means that we are double. This is size of the container, so that's half volume, which equals 2 times the concentration. So let's see what happens in this case. We are so thinking about sort of our little equilibrium here. We are going to be multiplying. We're going to be multiplying our N2 and our H2 power of 3. All of these are going to be multiplied by 2. And over here, we have NH3 raised to the power of 2, also multiplied by 2. So when we compare the multipliers on the left and the right, we can see that the 2 can kind of just pop out of the brackets here. This 2 pops out of the brackets as a 2. This 2 comes out of the brackets as an 8. These are multiplied, so we now have 16 times on the left, and the 2 over here just comes out as a 4. So we have 16 times our original N2 concentration and our original H2 concentration. I'm going to draw the line after. And we have only 4 times the NH3 concentration. So which way have we stressed the system? Well, we very clearly stressed it this way. Right? It's now way heavy on the reactant side. We have a way higher concentration. We have an effective 16-fold increase on the left versus a 4-fold increase on the right. So we're going to have to make some major adjustments to the amount of N2 and H2 in order to compensate for this huge change in equilibrium. So we're going to have to change, we don't know what these numbers are, but these numbers in here are going to have to change. So that means that the actual value, the concentrations of nitrogen and hydrogen are going to have to change in order to form, and the amount of NH3 is going to have to increase as well. So we're going to have to decrease these values, and we're going to have to increase these values. This means a shift is going to go this way. So we're going to go shift to right. Increase NH3. Decrease N2 and H2. So I have to decrease both those concentrations. So what is the effect on equilibrium if the reaction chamber is increased in volume while keeping the temperature and total number of particles constant? So if the reaction chamber is increased in volume, so let's say we were doubling it or tripling it, then we are going to be decreasing concentration, right? Decreasing. All right, so let's write this out. We are going to be increasing volume, which equals a decrease in pressure, which equals a decrease in concentration. So in this case, we are going to be getting that same sort of action here because we have those N2s and those H2s to the power of 3, and we have NH3 to the power of 2. When we go to decrease the concentration, whatever change we have over here, we get a power of 4, so we got a fourth order, overall fourth order, 1 plus 3, fourth order change. Over here, we have second order. And what do I mean by order? I mean these values up here. So if we just think about adding up our exponents, then they add up. Then if you think about it this way, then any change is a fourth order change. This is a very rapid change versus a second order, which is a slower change. For you math heads out there, in terms of order, we think about first order, first, second, and then there's third, and then fourth, etc., up into infinity. So the quicker, the higher the order, the faster the change. So whatever this is, so this is the amount of change. This is we could think about this as concentration. This is the effective change. The effect is much, much higher for small changes. This is not a great graph, but that's okay. So what I want to conclude here is that that the change, an increase in volume, will have a much greater effect on the reactants because of the higher order exponents, which coming from the larger coefficients reaction. And then so in this case, we are talking about increase in volume, which is decrease in concentration. So this large decrease in concentration of the reactants slows the forward reaction down, so the product gets converted back to reactant quicker than product is formed. Yes, 11 o'clock is our time. Okay, we have 10 minutes left. Can I explain temperature changes in 10 minutes? Let's see. Give me a chance, and I will try, of course. We have to conclude. This is, so shift is to the right. Okay. So recalling from kinetics that increasing temperature always increases the rate of a reaction. However, increasing temperature always increases the rate of an endothermic reaction more than an exothermic reaction. So thinking back to our chemical reaction diagram, if I have a reaction that looks like this, the mirror image, so if this is our forward reaction, right, this is forward, the sort of mirror image to this is something that looks like that, right? This would be our reverse reaction. So if this is exo, this is endo. So when you go to increase the chemical the chemical reaction temperature, you will have a different effect on the forward and the reverse reactions, because for the reverse reaction, which is endothermic in this case, it will be actually increased a little bit quicker when you add more temperature. Another way to look at this is to think about the heat as being part of the reaction process. So this is our endothermic reaction here. Endothermic heat is reactant. I'm going to write that better, just one second. So endothermic. And in the endothermic, we have heat is a reactant. Heat as a reactant. And then in the exothermic, we have heat as a product. Is product. So again, thinking about our teeter-totter, if we increase the temperature, increasing the temperature causes the equilibrium position of a reaction to shift depending on whether it absorbs or releases heat. So decreasing the temperature will also cause the equilibrium position of a reaction to shift in a direction that releases heat. Okay, yeah, okay. So let's think about this. So for an endothermic, we have R goes to, or R plus heat, and that goes to product. So increasing the temperature, so if we increase T, then we are effectively increasing the amount of heat. So our tipping point is going to be like this. And so to balance, we have to form the new equilibrium, which is going to be more product. And that's actually going to consume some reactant, right, and some heat for an endothermic reaction. If we did this for the exothermic reaction, let's see if I can fit that in here in the next 4 minutes, exothermic reaction. We have a similar setup, but we have reactant, and we have product plus heat. So in this case, you're going to be increasing the heat by increasing the temperature. And so that means that the teeter-totter is now shifted this way. So in order to find equilibrium, we're going to have to produce more reactant at the consumption of some product and of that extra heat. So the reactant has gone up. Here the product went up. So an exothermic reaction will actually reverse itself under the exposure to heat. So this is a really interesting concept and one you can exploit to increase the rate of a reaction, or to create the amount of product, or to slow a reaction down sometimes. Decreasing the temperature causes the equilibrium position of a reaction to shift in a direction that releases heat. So same idea, let's set up our two equations right away. So we have our basic endothermic reaction plus heat gives us product, and we have our exothermic reactants gives us products plus heat. This will be end and X. So if we put them under a stress, and that stress is going to be temperature down, then we're going to be decreasing the heat here, In this case, it will now place the stress system like this. We have more product than we have heat to support, or the product is out of equilibrium with the amount of heat in the system. And in this case, we are going to have something that looks like this. We have a lack of heat compared to how much reactant we have. So the chemicals to shift, we are going to get something that has to balance that out. So here we had too much product, so we're going to decrease the product, and we're going to increase the reactant to make up some of that heat. And in this example, we're going to increase the amount of product at the use of some of that reactant to get some of that heat back. So shift left, shift right. And this one was shift right, shift left. Okay, how did we do? We have an example or two and some other things to talk about. So let's do those tomorrow, and otherwise we'll finish up for today. And ruminate on those. If there's some example questions later you can work on, then that would be great. Otherwise, go back and look at some of the examples from earlier and see how those are going. Okay, best of luck to you. We will talk tomorrow. If you'd like to talk to me, please don't be afraid to drop some questions in the Hangout anytime, and we can just have a little chat there as well. Okay, talk to you later. Bye-bye.